Rare events, yeah, it can be anything that is very rare happening in nature. For instance, what we do with this type of detector is we look for dark matter. Dark matter is everywhere around us. It's very abundant. We don't know what it is, so we build detectors to see what it is. And one type of detector is this dual phase xenon time projection chamber. So maybe I have to explain a bit what our detector actually does. What is a dual phase xenon time projection chamber? So dual phase, well, xenon is xenon. That's like argon and neon. It's a noble gas. And dual phase refers to the fact that we have it present in our detector. It's a cylindrical vessel, and we have it present mostly in the liquid phase, but there's a thin layer of gas on top, with two phases, liquid and gas. Okay, so that's dual phase xenon. But now what's the time projection chamber? What happens? So when a particle interacts with the xenon, it bumps into the xenon basically, then light is created. Also electrons are created in this interaction. And these electrons we drift through the detector. And when it arrives at this gas phase, so actually we drift up to the gas, and when it arrives at the gas phase, another light signal is created. So we have two light signals. And these two light signals together, they are a measure of the amount of energy that was deposited in the collision. So that's how we can retrieve how much energy was deposited. And not only that, the ratio of the size of the S1 and the S2 signals are a measure for the type of interaction that happens. So in this way, we can also do some type of particle discrimination, which then eventually is some type of background reduction as well.
Thesis.
Yeah, so when we're trying to look for rare events in the detector, it's extremely important that you understand your background signals very, very well. So basically, in essence, what I've done, all the work that I've done is related to understanding backgrounds in this detector, or not even in the detectors that we currently use, but also in their successors that are planned to be built. What can we do in order to make backgrounds as low as possible, in order to understand the backgrounds as good as we can? So I discussed this in the context of two detectors in practice. So one of them is the xenon Anton detector that we have in Italy, but also for its successor that still has to be built. This work is done in our lab here in Amsterdam, and this lab is called Xenon Amsterdam, and it's basically a research and development facility specifically for these type of detectors. What we need to do in general is we need to understand our signals very well. Not just background, also our real the signals that we want to see, but understanding signals is essential. And one thing that I've done is that in this XAMS detector, we've installed new types of light sensors, PMT, photomultiplier tubes. And we've done an extensive characterization campaign to see if these light sensors might be the go-to for the next generation detectors like the one in Italy. And we found actually that it's a very, very promising candidate. It's completely different than the one that we're used to using. Just to mention one thing, it's not a round faced sensor, but it's a square. But it's also very flat, so it has a lot of advantages that we try to exploit and characterize and see if we could actually use them. And we saw that it's a very good working, promising candidate.